Madalyn, thanks so much for joining me on this episode of Concentrating on Chromatography. I appreciate it.
Yeah, thanks for having me, David.
Just to start off, would you mind introducing yourself to the audience?
Sure. Hi, everyone. I am Madalyn Radlauer. I am currently an associate professor of chemistry at San José State University in San Jose, California. It's a primarily undergraduate minority serving institution, and I've been here now for almost 9 years. Before this, I grew up in New Orleans, Louisiana, so I'm not a California native, but I was very fortunate to end up in California for both my undergraduate and graduate education at Stanford and Caltech, where I studied a lot of catalysis, polymerization catalysis, both with Bob Weymouth and Teo Gapier. And then I went off to Minnesota and actually took my partner with me. He's a native Californian, so I took him with me to Minnesota, where I studied a lot more about polymer chemistry with Mark Hillmeyer at the University of Minnesota. And then luckily found this position and was able to come back this way, and I've loved it. So happy to be here today to talk about our research and a little bit about my group.
That's great to hear. Yeah, I was personally so thrilled when ACS booked a New Orleans event a couple of years ago. I was thrilled to have an excuse to go there. But yeah, you've certainly been all over the place.
Except the East Coast, which is where you are.
Okay, yeah, no, except the East Coast. Yes. No, please come. What drew you to chemistry originally and then eventually to organometallic catalysis?
So my parents are actually both lawyers, and so that was something that I knew about higher education, but I didn't really know about science higher education at all. And that was one of those things of they were really supportive. I had Miss Frizzle and Bill Nye the Science Guy getting me into science at a young age. And I guess I'm dating myself a little bit with that, but that's cool. Magic School Bus for the win. I love doing science and science projects. And I actually had a really amazing high school chemistry teacher, which I think is a pretty common refrain for chemists. We had this great chemistry teacher in high school, and she got me into doing a few projects. So I actually did a little independent research project with her, and I had done some chemistry at the University of New Orleans. We had some family friends who were there and working in the chemistry department and material science. And they said, "Oh, we have a summer program that you should apply to." And so I applied to the summer program. I eventually got into organometallic catalysis because of a professor at Stanford who Bob Weymouth, who I had taken organic chemistry with him and gone to office hours. And this is just one of those, hey, all students go to office hours. Your professors like want to see you. They really do. You're sitting in an office being like, am I not approachable? And it's just way more fun to hang out with students and talk science. And so I asked a lot of questions, and I was often the only person there in his office hours. People would typically go to the office hours of the TAs and not to the professor office hours with kind of a bigger school. But I went to his office hours a bunch, and we actually ran into each other at the San Francisco airport after I had declared chemistry. And he came up to me, he's Mad Rad, how's it going? And I was like, hi, Professor Weymouth. And he said, I just declared chemistry. And he said, oh, you should come talk to me about doing research in my group. And his group is focused on organometallic catalysis and polymers. And he taught me about both. And he encouraged me to go talk to other faculty, but we really clicked and I was really excited. So I got to do chemistry with him the rest of the time that I was an undergraduate. And then I was really hooked on catalysis because it is an inherently green method, right? Like when you use a catalyst, you're lowering the activation barrier, you're increasing the oftentimes the selectivity of a reaction, decreasing the amount of energy it takes. Sometimes you're decreasing the number of like protections or deprotections that are needed. There's so many ways that it takes a chemical process and makes it more accessible and more direct to what you want. And that just was so exciting to me. And so I continued to pursue that. I ended up on projects that were polymer focused, like polymerization focused. So we were chaining molecules together to make these really long macromolecules. And I didn't actually know that much about them. And so I'm thinking about kind of an embarrassing story. It's not embarrassing. It's just I didn't know, and I had to learn. But I had taken GPC and gotten GPC results, gel permeation chromatography results that was on these polymers, but I didn't really know polymer chemistry that well. At some point, I was asked about SEC, size exclusion chromatography. GPC is a type of SEC, but I hadn't put those two together because I wasn't constantly in a polymer space. I was in a catalysis space and an inorganic space primarily. And so GPC was an acronym that felt natural. And so somebody then asked me about SEC, and it was in my postdoc interview, and I didn't know. And I faked it through and asked a follow up question and then realized, oh, he's asking about GPC, and then was able to get into it. But it was one of those moments where I was like, wow, this is an area I don't really know. But part of the reason why I was interviewing with Mark Hillmeyer to go to his group was because I had done polymerization catalysis for a while and felt like I needed to learn more about polymers. And I felt like in some ways that moment of not knowing that GPC was a type of SEC is a really good moment of saying, yes, this was a really good postdoc to go into because I had a lot of things to learn. I came back to catalysis in a sense. I had done actually a couple catalysis projects with Mark as well, focused on olefin metathesis and ring opening metathesis polymerization, and also exploring some ring opening insertion metathesis polymerization methods with ruthenium catalysts, so Grubbs catalyst. But that wasn't really the focus. I focused a lot on some very fundamental polymer science, which was excellent. It was a good complement to what I'd been doing. But when I came back to it, I was just so excited about the questions that you can ask with catalysis. Like, how do you make something work more specifically and work more efficiently and potentially even enable a reaction that could not happen otherwise? That's where I went when I started writing the proposals for my research group.
To go all the way back to the beginning, as you noted, we're getting older because I understood all those same references. I think it is too bad, and maybe I'm just like disconnected from it, but I feel like the current generation doesn't really have that equivalent like we had with Beekman's World and the Magic School Bus and Bill Nye. I don't feel like there's anything in there, but maybe there's something else on YouTube that I'm missing that's really taken over that spot in terms of inspiring young scientists.
I think that there are a few good ones out there. So I have two kids, and we actually watched some of the classic Magic School Bus together. But they actually rebooted Magic School Bus at one point, and those are pretty fun. But the old ones stand strong, just like they've rebooted recently Reading Rainbow. Right? Some of those especially great educational shows are coming back. And if you're thinking about biology and ecology, you've got the Krapp brothers and their creature powers shows. So I think there's some good things out there. And then there's one called Emily's Wonder Lab. So you do have a couple of shows and opportunities out there, but I'm pretty biased. I don't know that you can really beat classic Magic School Bus. So
Yeah, and that's certainly somewhat of the inspiration of this podcast, I would say, is to highlight the important work that's being done in a way that might be somewhat more easy for the general public to understand, certainly speaking to a lot of chemists themselves. But my other hope is that someone who's not a chemist or who has been removed from their academic career could watch or listen to one of these episodes and get something out of it, and certainly focusing on the importance of the science, because I think that's the other disconnect that sometimes exists, is that you're doing such critical work, but if you get too buried in some of the technical details, you lose some of the focus on the why is this important.
absolutely. Absolutely.
So you talked about building your research group, but I'd love to hear about anything you'd like to share about that process, but also what are the big scientific questions that you're trying to answer?
I'll start with the second part of that question just because I feel like it pulls from my previous answer. I got really excited about continuing these questions about catalysis, thinking about what are some really difficult reactions to catalyze or to catalyze specifically. And so I had done all this work in polymerization catalysis, and actually there are a lot of polymerization catalysts out there. There's some Nobel Prize work from the Ziegler-Natta catalyst side of things. So those are like group 4 transition metal chemistry, which actually makes a lot of the like commercial plastic that we use, especially polyethylene and polypropylene, is made by catalysis. So we have a lot of great catalysts out there already. And so I didn't really want to focus on polymerization catalysis. But in doing some fundamental polymer science work, I got excited about polymers as a scaffold for catalysis. It's almost like if you're building a building, it's a lot easier to build more complex structures if you have scaffolding access to different parts of it. And it's the same idea of, hey, could I actually have a structured polymer, something that at the molecular scale is going to change access to the catalyst? Could we then change the way that these molecules interact? And this is actually not a new idea. Nature does it. I feel like enzymes are a perfect example. You have that giant proteinaceous scaffold and then those small active sites, but it's the scaffold and those allosteric sites that control the activity and the specific microenvironment. So like I said, down to the molecular level, what molecules are accessing those transition metals in a metalloenzyme. It's also something that's not new because people do catalysts on different structures oftentimes it's less about the type of structure, but almost any heterogeneous catalyst could be supported on silica or supported on alumina, and so you have those examples as well. But because I was looking at polymers very specifically, I started to get this perspective of, hey, people are making these polymers known as single chain nanoparticles. And they've now actually changed names. People call them a variety of things. But I like the term single chain nanoparticle because I think it does give us a really good picture. A polymer is a really long chain molecule. So with tons of made up of repeating subunits. And if you just have what we call a linear polymer, when you think linear, you think a line, but that's not what entropy thinks, right? There's disorder. And if you actually have a linear polymer chain, it's usually not rigid. There are rigid polymers, but that's not what I'm talking about in this case. The polymers that we think about on a regular basis, the plastics that we think about, polyethylene, polypropylene, polystyrene, those aren't rigid backbone polymers. And so they actually collapse. And when you talk about proteins, you might talk about folding, but these aren't quite so neat. So they collapse onto themselves. And how they collapse depends on whether or not they are in solvent or in the melt with other polymer chains. And so they'll actually entangle with other polymer chains. There are a ton of different analogies that people use. Some people talk about like spaghetti on a plate. I like the idea of that drawer of airline earbuds where everything's tangled together and you can't extricate one from another. But basically, like, the idea is that these will tangle with one another. If you have it dilute enough and you have some sort of way to tie pieces together, which we'll call cross-linking, you can actually have a single chain collapse and then tie it to itself to make a structure of some sort. And it's not necessarily a well-defined structure, but it is collapsed into a single particle. If we could support a metal center in there, that is analogous to a metalloenzyme. And so that I think is really cool. And if we could control a little bit more particularly what types of monomers are near that metal center, well, then you're starting to control the microenvironment. And so this was something of, hey, can we think about controlling the microenvironment with polymer structures such as single chain nanoparticles, but we also look at star polymers in order to change the type of reactivity that's possible. And the reason why we think this is so interesting is that Most of the time, if we're talking about homogeneous catalysis, so catalysis in a like kind of in solution, we think about a single small molecule kind of in there catalyzing the reaction, but it's interacting with solvent, it's interacting with reagents, it's interacting with product, because product is still in there unless there's some way that you're actively separating it out as you go. And so by putting it into a polymer framework, we might be able to alter what it interacts with or what conditions it's okay with interacting with. And there's some groups that have shown that this is possible, but I think that there's still so many unanswered questions with that. The other big question from my group actually comes from, how do we understand what's going on in this not that well defined collapsed structure? One of the crazy things about polymers, and since this is about chromatography, we'll definitely get into this a bit more later. When you make a polymer, most of the ways that we make polymers, we are not making polymers that are of the exact same length, have the exact same number of repeating subunits, because that's really hard to control in the ways that we build polymers. So as your chain, if we do an enchainment reaction where we're basically pulling monomer after monomer, if one chain starts slightly after another, they'll have a different number of monomers. Or if the mass transfer in the reaction is not good, they'll have a different number of monomers. But even if it's just out of, in terms of mass transfer is going well, you have good stirring, you have good mixing, you have, which I guess are roughly the same thing, you have a very fast propagation reaction or a steady propagation reaction, even then you're going to have some what we call dispersity in the size of the polymers. And this is something that we can measure with chromatography in a way that we can't really measure with anything else. And so that dispersity means that inherently these structures won't be exactly the same. When nature makes its enzymes, typically it does not have that dispersity. It's monodisperse, precisely like only one. It's not monodisperse where it's just one peak, but like it's one mass. This protein has this number of amino acids in this exact structure. And that's not usually how we do it on the synthetic side. And that's also why I'm really interested in it, because the synthetic polymers are much easier to make than the proteins, especially if we want to vary it and do all sorts of crazy things. Now, I have a feeling the biochemists who are listening to this are like, we can make proteins, we can get yeast to do it, we can get E. coli to do it, it's easy. And I'm awesome. I'm talking about grams and grams of material, and that's different. And so I think we have an opportunity to make grams of material to then make a slight change and make grams of material. And we can do that on consecutive days. It's not something that we have to spend months doing if we want to make grams of material or if we want to make tons of different changes. And I think it actually helps us answer different questions. But yeah, so to come back to it, they're not exactly the same. And so how do we deconvolute any changes that are happening because of the polymer structure rather than changes that are just happening because we're doing the chemistry in this lab or we're doing the chemistry in this way? And so from the very beginning, we're really interested in this idea of benchmarking our reactivity, finding reactions that have been done maybe not very successfully, maybe with low selectivity, maybe with low yield, or maybe ones that work very well so that we can start there and have low-hanging fruit. But look at those catalytic reactions and try them with a small molecule catalyst before we try them with these supported catalysts or before we try them with an altered catalyst. And a small molecule catalyst that's right out of literature or even something that's commercially available. And this idea of emphasizing benchmarking as a way to differentiate where different effects are coming from is something that I've gotten really excited about and something that has become more and more central to the work rather than something that was like, well, we have to do this. This is just something we need to do. And now it's something that is like, oh, actually, this is something that is interesting scientifically and is going to come up with other results that people need to hear and need to do. And so this has become more and more central to our work. So those are the big kind of scientific questions. But you also asked about building a research group at San Jose State. This was really exciting for me. I went to some big research-focused institutions, and I found that the times that I was having the most fun was when I was working with other people in the lab. And I really wanted to continue that. I had mentored several undergraduates as a graduate student myself. I had mentored several undergraduates as a postdoc. And I had this plan that I wanted to go to a primarily undergraduate institution so that I could keep spending time in the lab and keep having those experiences where students are connecting the things they're learning in classes, the things that they're interested in, things that are going on in current research, and things that they can do in the future. And making that, oh, I am a scientist and I can chart my own path through whether it's research or and it could be with undergraduates, it could be anything, right? I have undergraduates going to medical school or pharmacy or but I also have students going to a PhD and students going straight into industry jobs. And all of these are success pathways because it has to be what the student wants. But I think what's really exciting is in the research lab, they all get this opportunity to see themselves as an independent scientist and to build up the skills to be an independent scientist. And I really enjoy being part of that process. And I've had a very large group. When my group first started, we had 12 people, and the largest it's ever been is 23. Um, we do have master's students as well in the chemistry department at SJSU, but I actually don't just have chemists in the group. I've had biology majors, forensic science majors, chemical and materials engineers, and even biomedical engineers. So it's a little bit broader, and chemists and biochemists. It's a little bit broader of background that they come in with, and then they end up asking different questions or being more excited about different aspects of the research. And that's a really cool thing. So I have trouble saying no to someone who gets excited about the science we want to do and excited about working together. And it's a lot to manage, but it's been a lot of fun.
That's great to hear. And certainly in the future, as those students produce exciting projects that you'd like to share with an online audience, feel free to send them my way and I'd be happy to interview them about a specific project or anything that was
Oh, very
going
cool.
on. A moment ago, you noted star polymers, and I thought one thing that was pretty cool, not to put words in your mouth, but it sounded like the approach you took went against the grain in terms of what the literature said you should do. Would you mind explaining that a little bit?
Sure, sure. So star polymers are another type of structured polymer. There are a number of different ways to make them, but one way to think about it is that they are a bunch of polymer chains tethered together at the core. And you could have a core that's like a single molecule and then build out from there. That would be called a core first, a star polymer synthesis. But for us, what I was really interested in was making an arm first. So where you make these polymer chains, linear polymer chains, and then you connect them through cross-linking reactions to make the core. And so I imagine that, like, I think of that more as like a pom-pom look when I think about, make sure you're thinking in 3 dimensions when you're thinking star polymers. So this is a technology that had been developed kind of decades before I had started at my current position. And so I was like, okay, star polymers, we're going to make them. The important thing about making an arm for a star polymer is you need to use a polymerization method that allows you to purify the arms and then restart polymerization so you can do those cross-linking reactions. And to pull them and tie them all together into the star. And people had often used controlled radical polymerizations, specifically focusing on nitroxide mediated polymerization or atom transfer radical polymerization, so NMP and ATRP. And folks had not used RAFT, or reversible addition fragmentation chain transfer polymerization, also a controlled radical polymerization, as much for this. There were some papers, notably from the Boyer lab, and where they saw that they were able to do star polymer synthesis with Raft. And then there were some other groups that built off of that. That was in 2011. So that was before I was a faculty member. And I just went with it. I didn't realize how hard it would be with styrenic monomers so styrene and substituted styrenes, to make star polymers with Raft. But the reason I really wanted to use Raft polymerization was because the whole reason to do this was to, in my lab, was to embed those ligand precursors and metal so that they could connect to those metals, and then we'd have our metal complex in the core of the star polymer, protected from what's going on the outside. There's a really cool paper from Hawker and Frichet where they used nitroxide mediated polymerization, so NMP, to do this kind of thing. And they put a organic basic catalyst in one and an organic acidic catalyst in another, and then they combined them and they did tandem catalysis, where the first reaction was acid catalyzed and the second was base catalyzed, or maybe it was the other way around, and got the final product only when they were both supported in these star polymers. And so the acid and the base couldn't reach one another. And I was like, this is a great reason to use polymer structures to enable catalysis. And tandem catalysis is, in my mind, one of the coolest things, because you're running multiple reactions that may or may not be compatible with one another at the same time. And so if you're not using something to protect your catalyst, or using some very complicated engineering, you have to run one catalytic reaction, purify or take out the catalyst at least, and then run the next one. Or move it from one reactor to another. And wouldn't it be so cool if there were things that we could do where we didn't have to isolate that intermediate? Because sometimes the intermediate is really reactive or really toxic, or you can think of all sorts of reasons why we might not want to. And then, of course, there's more separation science needed at that intermediate step if you do have to separate it in order to do the next thing. But that takes resources, it takes time, it takes potentially solvent, so there are a lot of reasons to not want to have to do that. And it just makes it a more green process if we can move straight through. And so I wanted to be able to incorporate phosphine ligands, NHC ligands, those are N-heterocyclic carbene ligands. I wanted to be able to incorporate ligands that had amines, or ligands that had imines or amides, or all these different things that would, for example, bind to copper. So that takes ATRP out of or many of the metal required ATRP out of the running. And then I wanted to be able to add in things that could be oxidized, and nitroxide mediated polymerizations are less favorable for that type of thing. And I was like, Raft is going to be excellent. It has really high tolerance. That's the way we're going to go. And it was one of those things where we were like, okay, well, we're getting some cross-linking. This is working, but it certainly did not work the way that NMP and ATRP promised. And initially, it didn't even work the way that the acrylate polymer work had promised. And so we were a little, oh shoot, is this even a possibility kind of moments. And I think what really turned things around is we just dug into the literature a bit more, spent a little bit more time thinking about what are the things that we can alter. And one of the things that was really important was actually, when I started, we only had access to refractive index detectors for our GPC, so for gel permeation chromatography, which is giving us our molar mass and our dispersities. We only had refractive index, and that refractive index was showing that we had a peak for remaining homopolymer, and then a second peak actually coming out at an earlier time for our larger cross-link polymers. In GPC, the larger the polymer is, the earlier it comes off, because it can't explore as much of the volume of the size exclusion column. And so we saw that peak, and so we said it's working. And it wasn't until we got a new instrument that had a light scattering detector that we realized that we were actually only, I think maximally we were getting like 5 chains together. And in order for that star polymer to really be protecting the core, I was like, oh, we're looking for tens of polymer arms being pulled together. We're not there yet. So it also was a moment of, I wasn't getting enough information out of the RI. And so it was as soon as we got our new instrument, we were able to see that, oh, we haven't hit that bound that we need yet. And so that was something that we dug into further. And we've been able to pull that together and put together a really nice set of parameters. And now we're making star polymers with a variety of different monomers, styrenic monomers, acrylate monomers, acrylamide monomers. And we're able to keep using our light scattering, the combination of refractive index and light scattering, to have a good understanding of the material we're making. And then also we're learning how to purify those with dialysis to get rid of all of the remaining homopolymer. There's a lot of pieces to that project that ended up being more complicated than I thought it would be from the beginning. But at the same time, we have shown that we can incorporate these really cool ligand precursor monomers with phosphines, with imines, with amines. So there's a lot there.
It's so cool to hear from researchers like yourself when, and I'm not necessarily saying that you're claiming to be the first, but certainly there's are some instances where it's like there's no published record of this approach being used for this, but we're going to do it. We're going to see if it works. And then being able to claim, like, hey, we have the data to show that this is the first time this has ever been applied. It's just super cool.
Well, I think, unfortunately, what happens is when things don't work well, it often gets buried in, if it's published at all, it's buried in less important publications. And so there was a paper that I finally found that said, basically, don't use raft for styrene star polymer synthesis. And I was like, I definitely didn't find that when I was writing my proposals. I'm glad I didn't. Sometimes it's good to not find the thing that tells you not to try. But at the same time, I wish I had found it to know that a little earlier, to know that it was going to be so tough. So I think I would have questioned the results from the RI a little bit stronger and said, this is something we really do have to be concerned about. And I think I saw that earlier peak and said, we're getting cross-linking, and was like really excited about that piece. And we've learned how to make that cross-linking a lot more. But one of the things that's tough, like we were talking about it before we started the recording, but there's so many papers out there. And you don't even always have access to all of them, even if you're at an academic institution. And so you might not find something if it's a little buried. And I thought I had done that very full search of anything that had the words styrene and raft and star polymer. I thought I had found everything, and most of it was on core first. In fact, like if you look out there for core first star polymer synthesis, like raft is used all the time. And I think that sort of biased me a little bit in the wrong direction of, oh, this is going to be straightforward, but going the other way, it's really not. And it's something that we've dug into more. And I think it has that kind of same feel as the benchmarking work that we're doing, thinking about, oh, benchmarking, it's just something we should always do. It's something that we will always help us contextualize our results. And I think that what happens is that's seen as less sexy in terms of research, because it's, oh, I'm repeating something that somebody else did to make sure that the results that I'm seeing that are different from what they got are actually from the things that I intended to change, rather than something that I didn't mean to change, but is different because we're in different states. And so the humidity is different, or different lab spaces. So I have sunlight coming into my labs and maybe you don't have sunlight coming into your lab. There are things that can change chemistry that we don't necessarily think about putting into our SOPs or into our experimentals. And like chromatography, oh, this column has been around for X number of years. We have to treat it differently, and our method ends up being a little bit different than yours. And so I think all of those questions, all of those moments of like, when I'm doing science in a different building, in a different lab, with different people, with different SOPs than you, I really do have to think about what are those little changes that matter. And I think with star polymers, that was like one of those moments of, hey, I'm looking at a different type of monomer, right? It's the styrenic monomers versus the acrylate monomers. And so there's been a lot of success with those acrylate monomers and even acrylamide monomers, but like styrene, not so much. And so this was one of those things where I learned the hard way, and my students learned the hard way, that it wasn't going to be straightforward, but we did get there. And I feel really excited that we have now so many knobs to turn and ways to use these methods going forward.
I was chuckling to myself thinking about a case, a municipal lab in California, where they'd reached out regarding some changes there in their evaporation process. And it was literally just that for certain times of the year during the warmer months, they would benefit from a chiller because the temperature of the water that they're using is just different in the summer. And that's changing how the condenser works and the rates. It's just, you might not think about it necessarily, but when that's just for one lab, one location. But yeah, anyone trying to replicate that somewhere else, it's just so simple, but obviously the different parameters would change the results.
Absolutely.
But I was thrilled to see that chromatography is used all over your lab, and you noted size exclusion chromatography, but I'd love to hear about how TLC and some other types of chromatography are applied as well.
Sure. So I think at our core, we are a synthesis lab. I've always loved making molecules, whether they're small molecules or big molecules. And I think it's really thrilling to do that essential chemistry. I don't mean that to say anything negative about any other chemistry, but when people think about chemistry when they're kid, it's combining stuff and making it change. And so that feels really fun. And as a synthetic lab, TLC is a great way to monitor reactions. So thin layer chromatography, a great way to monitor reactions and help us determine whether or not, so for example, we do a lot of ligand precursor synthesis on the way to making our metal-based catalysts. And so we will run TLC to see, hey, has our reaction gone to completion? We'll also run TLC to help us determine how to purify it if we decide to use column chromatography. And there's another type of column chromatography that I was introduced to by a colleague that I've really found I love. It's called dry column vacuum chromatography. And it's a preparative method, so just a silica gel column. And it requires a lot less solvent, it requires a lot less time, it requires a lot less silica gel. And we've found in our hands, it's been extremely effective. So I grew up, and that's a funny way to put it, but I grew up doing like very standard column chromatography. And I think I learned to do it really well and to appreciate the ability to use silica gel column chromatography to go from grams of impure material to grams of pure material. That feels so good. I know some people rag on column chromatography because it's time consuming and it takes all that solvent and then you're pumping down stuff on the rotovap. But like that moment of going from, hey, this was like a mixture of products to I have separated everything and it's beautiful is just lovely. That moment when you take the NMR and you're like, yep, it worked. So that's primo. But I would actually say that this dry column vacuum chromatography, I fully converted to that as much as possible because it really is a way of shortening the process. And you actually dry load your material onto a column and then use fractions of solvent going from polar to less polar. And it separates your material really effectively. So look, there are some really good online tutorials if you haven't checked that out. And if you're doing synthetic chemistry, I'm going to just like broadly recommend it to people to see if it works for you. So yeah, so I have TLC, we have silica columns. I think the chromatography we use the most is definitely GPC and as a type of size exclusion chromatography because of what it can tell us about polymers and polymer size. With the system that we use the most often, we can look at things that are hundreds of thousands of grams per mole down to things that are hundreds of grams per mole. And one of the great things about having different types of detectors, we have a refractive index, UV, and light scattering. And so the refractive index and UV give us really good ideas of how much we have of each one because their feedback is dependent on concentration. Whereas our light scattering, the size of the peak is more dependent on the size of the material. So the bigger it is, the more light it scatters. And so we can see even tiny things that are quite large, or tiny amounts of things that are quite large. But even if we have a lot of it, if it's very small, it still won't scatter a lot of light. So what's also really neat is with refractive index, you're using a conventional calibration where you have a series of masses and you plot out what times they come out, so what elution time they come out, what elution volume they come out, and then you have a fit to that. And then it's not a linear fit, but it's that same kind of picture of, oh, I have an equation, and so if I know at what time something comes out, I can then backtrack using that conventional calibration to what is the size of this material. But that's a relative measure because I talked about polymers collapsing. If a polymer is not as soluble in a solvent as another polymer, it will actually collapse tighter into itself. Whereas if the polymer likes the solvent, it will expand a little bit and allow more solvent inclusion in its collapse. And so you have to match your calibrants to, like, your standards to your products based on like how good a solvent the eluent of your instrument is for that polymer. And so if the eluent for the instrument is not good for the polymer, you can't get data. For example, we primarily run with THF, but you can't really get reliable data for poly N isopropyl acrylamide because it's too insoluble. So even though it is soluble, it tightens up so much that it always looks really tiny in THF. But if you put it on DMF or you put it in water, then it behaves very differently. RI and UV only give us these relative measures, whereas light scattering gives us a way to look at the absolute molar mass. And that's actually the different data that we got that gave us how big our star polymers actually are. Because one of the things about a structured polymer, something that has been cross-linked, is its size, its hydrodynamic size will change because you've tied it to itself. And so it actually can't just spread out as much or as loosely. It has to be very tight. Light scattering gave us a way of determining absolute molar mass, which actually gives us a way of looking at the number of arms per star that is much more reliable than the relative measure we're getting from refractive index. And so that opened up a lot for us in our research and has been really cool to learn more about and get more used to as someone who went from a synthetic, inorganic background, really inorganic catalysis focus. Now I'm learning about polymers and all of the different ways that we look at polymers. And now I'm trying to teach other people how to do that without ever having to take a course where I got a grade for understanding how GPC works, right? And so that's, you got to learn on the job sometimes. So we keep learning.
Totally. And I know we're running short on time, but if I could ask you one more question, I'd love to hear about the GCMS methods you're developing. And my understanding was that'll be applied to characterize products directly instead of relying so heavily on purification. What really motivated that effort?
So I've talked a decent amount about how benchmarking and being able to check reactions and make sure that what we're doing in our lab is turning out the same as what the, or at least is comparable to what has been reported previously before moving on to a new system or testing a novel catalyst. So this is actually for an olefin metathesis project. People have been studying olefin metathesis for a long time. The Nobel Prize for olefin metathesis, I think, was 2005. So it's a method that's been studied for decades. And there's a certain type of olefin metathesis. So this is a reaction where you have carbon-carbon double bonds, so alkenes, also known as olefins. And those alkenes end up switching partners, and this is mediated by a metal catalyst. And by switching partners, the alkene itself is, that double bond is cut through the formation of a metallocyclobutane. So it's a metal with typically 3 carbons. So you have a butane, but part of that is a metal. And then it switches which substituents are with the metal versus which substituents are tied to each other. And this is a really neat way of doing synthesis and introducing a new substituent to, or several new substituents to a molecule. And it's been used in agriculture and in fine chemical synthesis, just all these different applications of olefin metathesis, polymerizations. We're specifically interested in olefin cross metathesis, so where we're looking at small molecules changing partners and thinking about it as a route for the synthesis of fine chemicals or the synthesis of even like commodity chemicals. But one of the things that's tough about this, in terms of thinking about commodity chemicals, is that these catalysts often fall apart or degrade in some way before you get a lot of product. They don't run continuously for days and days. You maybe get 12 to 24 hours of activity, for example, for a ruthenium catalyst. And that becomes really expensive if you're going for something that would be a commodity chemical. But for fine chemicals, that can be totally reasonable, depending on how high value the product is. People have made all sorts of variations on, and I'm going to focus on the ruthenium-based catalysts. These are the Grubbs and Grubbs-Haveda catalysts. All sorts of variations, and then have studied them for tons of different reactions. But it doesn't seem, especially in cross-metathesis, they're studying them for that same reaction. We don't often see a benchmark. Oh, here we're going to take these really standard conditions, run this reaction the same way everybody else does, and show that this catalyst with these changes is getting the same selectivity in cross metathesis, or the same reactivity, or the same catalyst lifetime. Typically, when you read about a new catalyst, they've immediately changed the conditions. Oh, here are some brand new catalysts that can do high temperature, or here's some brand new catalysts that can do Z selective rather than E selective. And these are amazing, but how do we compare them? And what if we want to think about which catalyst would be the best at this or the best at this from this huge range? Well, you could test them all. And certainly many of them are commercially available. So that's something that's possible. But I think it would be really neat to have a method that's really low touch. Like, you're not going to do that much work, and immediately you're going to get an answer of, oh, this kind of compares this way. I made a brand new catalyst. I'm comparing it this way. And so we're interested in kind of the classification of olefins that was done by Chatterjee and Grubbs and a couple other folks in the Grubbs lab, where they thought about type 1 olefins homocross really fast, type 2 homocross slowly, type 3 don't homocross but will react with type 1 and type 2, and type 4 are hanging out. And this is catalyst dependent. And so they tested for Grubbs second generation, Grubbs first generation, and did some comparisons there. But now with all of these other catalysts out there, the way that they did this was they actually ran the reaction, ran column chromatography, collected and determined isolated yield, and for dozens and dozens of experiments. And that is an amazing amount of work. And the ones they picked were really interesting, in part because they picked things that were orthogonal to what could be done with palladium coupling chemistry, and like all these other reasons why to pick these chemicals. But what if I have a new catalyst and I want to do that? Do I have to then have my group of undergraduates run a ton of silica gel columns every single time we're going to test a new procedure, or test a different, like a change in conditions? Are we going to be running dozens and dozens of columns? And I didn't want that. And so I actually reached out to Arnab Chatterjee and said, hey, is this crazy? Do you think that if we went for a GCMS where we could do the separation and characterization at the same time, rather than separating for isolation and then characterizing by, say, NMR, do you think that would be a reasonable methodology? Was there a reason you didn't do that? And he gave me a couple reasons why they didn't do that, but none of them were, oh, this won't work. Well, in one case, one of the GCMS he would have used was down at the time he was focusing on this. And he was like, well, it's easy enough for me to run these columns. And they wanted to see isolated yields. And I get that. But they were asking a different question. They were asking solely about selectivity. And I'm asking about, can we benchmark this and can we get through it fast? And so he was like, that seems very reasonable. So we are actively trying to figure out how to use GCMS to effectively quantify this. So we have to think about the response factors and maybe find a good internal standard to work with for this kind of range of olefins that we're going to use as our test cases. But that's what we're shooting for now. So it's a fun project, and it's not, again, it's, I wouldn't necessarily say, oh, this is really fancy research, but part of the goal of it is at the end of the day, somebody else could take what we've done and just, oh, I'm just going to reproduce that in my own lab. I know the response factors based on what they gave me. I can use the same internal standard and kind of test my new catalyst. And we can do that in our own lab with our polymer supported stuff. Now we have a way of testing, and then we can throw it in and we can try different conditions. And where it's not every reaction is the 12-hour reaction plus the isolation plus the characterization. It should hopefully be, okay, we have our maybe even just 6-hour reaction, because maybe we don't need to run it as long if we're looking at selectivity at a certain time point. But we can try different time points even in an easier way, right? I don't have to run 4 reactions to try 4 different time points. I could try 1 reaction and get 4 different time points. If I'm just taking a small aliquot to clean out the ruthenium with a little bit of silica gel, just run, or alumina, run it over alumina, add my GCMS solvent directly to that to rinse everything off, make sure it's representative, and then throw it on the GCMS.
No, that makes perfect sense. Mal, this has been great. I really appreciate all your time today. Was there anything in closing that you would like people to know about your lab or your work that we didn't get to discuss yet today?
Yeah. Well, one of the questions that you gave me that we didn't have a chance to talk about was, what advice would you give to students interested in catalysis or polymer chemistry? And I think that this is one that I really love, not because I think I have spectacular or brand new advice. I think it's spectacular advice, but it's not brand new advice. The advice is to keep asking questions. I think Frizzle had this as part of her mantra, right? Ask questions, make mistakes, get messy or something. It was, but asking questions are so central to science. And one of the best things that I have gotten over the course of being a scientist in this kind of realm is the fun, exciting, interesting questions that we come across. And sometimes it's that moment where you're asking a question, you're like, surely this question has been answered, right? Like when we looked some of the benchmarking work that we've done, and we asked a question about auto oxidation for 3,5-diterbutyl catechol because we were seeing auto oxidation. And we're like, surely this question has been answered. Because it's such a clear one. If you take 3,5-diterbutyl catechol and you put it in solution, it turns yellow over time. So it's something is changing just with oxygen from the air with no catalyst around. So surely this has been answered. And it hadn't been. People hadn't studied this directly. And it was just one of those moments of, how many times does a student sit in a class and say, I'm not going to ask this question because surely everybody else already knows the answer, or surely it's not a good question, or it's already been answered, and I think it's okay to ask those questions as long as you're asking them earnestly. I think if it's a genuine question, like you genuinely want to know, it's a question worth asking. And I don't think we would be where we are in our research, doing the things exactly the way we're doing, if we weren't continuously asking the question, then doing stuff, then reconsidering our question. Was that a good question? Is that the question we want to answer? And sometimes you run a reaction and you get so focused on, oh, I have to get 100% of everything for this, or I have to be like really specific. And you're like, wait, pause. What's the question I'm asking? How will that be determined? And that's, I think, really cool, of like going back to the question over and over. I think it's the way to go. It's the way to do research. And in some ways, it's the way to keep going. And I see it in life everywhere, right? You have to keep asking questions.
Gemini says, take chances, make mistakes, and get messy is
Take
the
chances, make
catchphrase.
mistakes,
But
and get
yeah,
messy. Yes, love it.
but no, that's some great advice as far as asking questions. Absolutely. Mal, this has been wonderful. I really look forward to our next conversation and learning more about your lab. Thanks so much for the time today.
All right. Thank you.